Hi, I'd like to tell you about our work on signatures of primordial energy injection from Axion strings. My name is Joshua Benabu, and this is work with Malte Bushman, Shubhik Kumar, Eugene Park, and Benjamin Safdie. In this work, we place strong observational constraints on axion-like particle string networks. We do so by carefully studying the emission from axion strings of standard model particles that inject energy into the primordial plasma during the time of Big Bang nucleosynthesis, or later up until the time of recombination, or yet later up until the present day. By leveraging existing data on BBN, the cosmic microwave background, and gamma rays, we are able to place upper bounds on the axion decay constant. In this work, we are considering axion string networks which survive until at least the time of BBN, which require sufficiently light axion masses. And so in particular, we are not considering the QCD axion. We are working in the context of field theory axions, which are realized as the Goldstone bosons of a global U1 Pecha-Quinn symmetry, which is spontaneously broken at some high scale Fa. So we have our complex scalar field phi, the PQ field, whose complex phase is the axion and whose magnitude is the radial mode. And we are working in this scenario where the PQ symmetry is broken after inflation in order to give us axion strings. Axion strings are one-dimensional topological defects of the PQ field. And once they form, they enter a so-called scaling regime where the string length per horizon, psi, is roughly constant in time. If the domain wall number is equal to 1, then the string network survives until the axion mass is equal to the Hubble rate, at which point it collapses. And during the evolution of the network, the strings emit axions, and they do so with the rate, gamma A, which is set by the tension of a single string and the number of strings per Hubble volume, psi. However, axions interact weakly with the standard model, so this does not give they do not give strong observational constraints by considering the primordial energy injection. On the other hand, radial modes are also emitted by the network, and as they are heavy, they must decay promptly to standard model particles, though their emission is suppressed for frequencies less than the mass of the radial mode. We can see this visually from this plot of the energy density in radial modes extracted from one of our simulations, where we see short wavelength radiation of radial modes from a region of high curvature on one of the strings. In our paper, we motivate the conjecture that radial modes are emitted with a rate suppressed relative to the axion energy emission rate, but only by a factor of a logarithm of the radial mode mass divided by Hubble. In our paper, we motivate this analytically, but ultimately we confirm this with simulations. Our simulations solve the classical equations of motion of the PQ field on the lattice and use the technique of adaptive mesh refinement in order to ensure that the locations of strings are well resolved at all times. In this work, we also consider the direct emission of standard model Higgs particles from the network, which can occur if we have a quadratic coupling of the standard model Higgs to the PQ field, as this gives energetically stable Higgs profiles around the strings. Once we have determined the energy emission rates of the various particles from the network and their branching ratios to the standard model, we then know the total energy injected into the primordial plasma and can then use data to set constraints on Fa. For example, for string networks which survive until the time of the recombination, we explicitly computed the modification to the CMB anisotropy and used Planck 2018 data in order to set an upper bound on Fa around 2 × 10⁻12 JeV. In summary, in this work, we set strong upper bounds on the axion decay constant for ALP string networks from BBN, CMB, and gamma rays. For the details of our constraints on BBN and gamma rays, please see our paper. And looking towards the future, we believe that CMB probes will be an exciting future possible discovery channel for axion-like particles. Thank you for listening, and we hope that you'll check out our paper.